Hello, dear students. We are back again with another video lesson. In a previous lesson, we studied the magnetic force on a charged particle and the magnetic force on a current carrying conductor. When the current carrying into a straight conductor into the magnetic field, so this magnetic field experiences and exerts a magnetic force on this conductor. So you can determine the magnitude and the direction of the magnetic force on the current conductor. To find the magnetic force on a current carrying conductor, BIL sine theta. So you have to use this equation. This field is the external magnetic field, and this is the current carrying into the conductor, and this is the length of the conductor, and this is the angle between B and I. Its direction can be determined by using the right hand rule. The thumb is the direction of the current, and the four fingers, as usual, the direction of the magnetic field. And we have only one force. The force on the exerted by the magnetic field on the conductor is directed into the out of pump. Okay. The last topic in the in section 3 in chapter 5 is about the galvanometer. What is galvanometer? Galvanometer is a device used to measure very low current. Galvanometer is an electrical device that can be used to measure a very low current in order of milliampere and microampere. And also it's used in the construction of both a meter and voltmeter. A meter is a device that can be used to measure very high current, and the voltmeter is a device that can be used to measure very high potential difference. So can we convert galvanometer? This is like galvanometer. So we can convert galvanometer into a meter and voltmeter. Galvanometer is a device can be used to measure very low current in order of milliampere and microampere, but a meter can be used to measure high current. High current. Both a meter and galvanometer can be used to measure a current, but the difference between them is galvanometer measuring low current, a meter measuring high current. And voltmeter is a device that can be used to measure high potential difference. High potential difference. Okay. Voltmeter, a device used to measure potential difference. A meter, a device used to measure electric current or high current. What are the main parts of the galvanometer? The galvanometer is a device, and it consists of many parts. So the main parts of the galvanometer, it consists of what? A coil of wire. Okay, we have a coil of wire wrapped around a soft iron core mounted so that it's free to pivot, because the needle must be deflected, okay, into the maximum displacement and return by the severing into the original point. And also the second component of the galvanometer is a magnetic field or external magnetic field or a permanent magnet. We have what? A permanent magnet and coil of wire and the magnetic field provided by the permanent magnet. And the third part is spring. So the function of the spring in the galvanometer, when the current carrying into the galvanometer, this current produces a torque of the needle, and the needle as a result deflected by this current. So after the current is removed from the galvanometer, this needle returns to its original position. It will return to zero by spring. Okay, when the current is removed, how the needle of the galvanometer deflected to the zero? Because of the spring. So, and also we have a deflector and needles. What physical principle is galvanometer's operation based on? The galvanometer operation based on what? On the electromagnetic force. Is based on what? Electromagnetic force or torque created by a magnetic field on a current carrying wire. So when the current is inputted into the wire or into the galvanometer, we have a coil of wire, and also we have a magnetic field of a permanent magnetism. So this magnetic field exerts a magnetic force on the needle of the galvanometer, and it goes to deflect, and it goes to measuring the amount of the current. So when the current is, for example, when the amount of the current is more, the deflection of the needle also becomes more, and it deflected deflected more. Okay. Why sometimes we need to convert galvanometer to a meter? Because a meter can measure a high current. The difference between galvanometer and ammeter: galvanometer can be used for measuring low current, but ammeter measuring high current. So here we have some tips and some notes about the galvanometer. The torque experienced by the coil is proportional to the current in the coil. So this means that the larger the current, the greater the torque, and the more of the coil rotate before the spring tightens enough to stop the movement. If you remember in chapter 2, we studied that torque is equal to what? Fd. Okay? But in the galvanometer, the force is magnetic force. Okay? So the relation between torque and magnetic force is directly proportional. When force is more, the torque also is more. More force provides more torque. And this magnetic force on a current conductor is equal to what? B-I-L. Okay? So when the current gets higher, what happens to the magnetic force? Magnetic force also gets higher. Why? Because the relation between magnetic force and current is directly proportional. By increasing current, what happens to the magnetic force? Increases. By increasing magnetic force, what happens to the torque? Also increases. So finally, can we say that the amount of the torque or the deflection of the needle of the galvanometer is directly proportional to the torque? Yes, of course. The relation between torque and current is directly proportional. The amount of deflection of the needle is proportional to the current in the coil. In galvanometer, electrical energy converted to mechanical energy. We will give the electrical energy, and this electric energy converted to mechanical energy. When there is no current in the coil, current is zero, magnetic force zero, torque also zero. The spring returns the needle to what? To zero. Okay, so what is responsible to return the needle into the zero? The spring. Without spring, the needle, after the current removed from the galvanometer, the needle does not return to the zero without spring. But in the presence of the spring returns the needle to the zero. Galvanometer can be used to measure very low currents, as I mentioned, of order milliampere and microampere, and also can be used to find the direction of the current. What factor affected the torque produced by a coil in a magnetic field? Depends on the current carrying wire. More current, more torque. Now let's convert galvanometer to ammeter and galvanometer to voltmeter. At first, convert galvanometer to ammeter. Convert galvanometer into ammeter. How can we convert galvanometer into ammeter? Ammeter to measure high current. This could be done by connecting a resistor. Connecting what? Resistor. Of what? Of very low resistance. A resistor of very low resistance. In which connection? In parallel connection. This is very important, guys. Be careful. Once again, listen carefully. How can we convert galvanometer into ammeter? This could be done by connecting a resistance with a resistor of a very low resistance in parallel connection with what? With galvanometer, which is called shunt. This very low resistance is called what? Shunt. Okay? For example, when the total current, this is I total, is connected, like this is galvanometer, and connecting a resistor with a very low resistance is called shunt. This is RS. What do you mean by RS? Shunt. Very low resistance connecting in parallel. What is the type of connection here? Is parallel connection. Okay, so many students are struggling with the parallel connection and series connection. Guys, look, in parallel connection, and series connection. In parallel connection, for example, if we have three resistors and connecting in parallel connection, this is the source, okay? Three resistor, 1, 2, 3. This connection is parallel connection. In parallel connection, the amount of the potential difference are equal. This is V total. This is V1, V2, V3. This is potential difference across the source. This is potential difference across resistance number 1, R1. This is potential difference across R2. This is potential difference across R3. In the parallel connection, the amount of potential difference are equal. V total is equal to V1 is equal to V2 is equal to V3. For example, if the V total is 10 volt, how about V1? Still 10 volt? Yes. V2, 10 volt. V3, 10 volt. It means that in parallel connection, potential difference doesn't change. Potential difference is constant. Okay? But the amount of current, I total, so we have to add up the individual currents that passes through the individual resistors. Okay, is equal to I1 plus I2 plus I3. I total, how can we get I total in the parallel connection? We have to add up all the individual currents through the circuit. How about the series connection? In series connection, guys, look, like for example, if we have a potential difference and 3 resistors connected one by one, so this is R1, R2, R3. Okay, here if in the parallel connection, guys, look, if I total is equal to 9 ampere, if the resistance are the same, I1 is equal to 3 ampere, I2 3 ampere, I3 3 ampere. So if we add up all of them, we will get this 9 ampere. But in series connection, the situation is completely different with the parallel connection. If you have 3 resistors, the same resistor, but in series connection, in a series connection, instead of potential difference, what is constant here? The current is constant. I total is equal to I1. This is I total. I2, I across the third resistor is equal to I1, I2, I3. So how about the potential difference? Potential difference in series connection, how can we get the V total? By add up all the individual potential difference. V1 plus V2 plus V3. So the difference between series connection and parallel connection. Okay? In parallel connection, guys, once again, listen carefully. In parallel connection, potential difference are constant. The total current must be added to find, add the individual current to find the total current. Okay? But in series connection, the current, currents through the circuit is constant. I total is equal to I1, I2, and I3. But V is not constant. Guys, look, in parallel connection, V is constant. V is what? Potential difference is constant. But in series connection, current is constant. Okay, now I'm going to tell you why in convert galvanometer into ammeter we have to use a very low resistance in parallel connection. Guys, according Ohm's law, V is equal to what? IR. What is this? This is Ohm's law. I is equal to what? Is equal to V over R. Okay? What is the relation between I and R at constant voltage, at constant potential difference? The relation between I and R is inversely proportional. For example, low resistance provides more current. Ammeter is a device that can be used for measuring high current or low current. High current. What we need here, guys, we need ammeter to measuring what? Measuring high current. How can we obtain high current? By connecting a resistance with very low resistance in parallel connection to the galvanometer for getting more current. Why? Because according Ohm's law, in a parallel connection, guys, in parallel connection, V is what? Constant. When V is constant, if resistance decreases, what happens to the current? Current increases. Okay, so that is why we have to connect a galvanometer with a resistance with very low resistance shunt in parallel connection. Okay, how can we convert galvanometer into ammeter? Ammeter is equal to galvanometer plus what? Resistance with very low resistance. Low resistance in parallel or series? In parallel. Why? Because in parallel connection, V is constant, I and R inversely related. What the shunt's function draws most of the main current and leaves only a very small current to pass through the galvanometer, which could be measuring easily and measuring high current. The second construction of the galvanometer can be converted into a voltmeter. So this could be done by connecting a resistor, very high resistance. How can you convert galvanometer into a meter? Connecting a resistor with a very high resistance, but in series connection. Why? Because to convert, guys, look, convert galvanometer into a meter. Voltmeter is equal to galvanometer plus a very high resistance in series connection. Why? Because according Ohm's law, V is equal to what? IR. In series connection, guys, in series connection, which one is constant? I or V? I is constant. In series connection, the amount of current throughout the circuit is constant. Okay? When current is constant, what is the relation between R and V? Directly proportional. More value of resistance provide more potential difference. And the voltmeter can be used to measuring high potential difference. What we need? We need high potential difference. For getting high potential difference or reading high potential difference, we have to connect a resistor with a very high resistance, but in series connection. Why? Because in series connection, current is constant, and the relation between V and R is directly proportional. More resistance provides more potential difference. Very high resistance in series with the galvanometer. Voltmeter is equal to galvanometer plus resistance with very high resistance in series connection. What is shunt? Consists of a resistance, very low resistance in parallel connection with the galvanometer to convert galvanometer into a meter. Okay, so this is some notes about how can you solve the questions in a meter. The resistance must be connected in parallel, and in parallel connection V is equal, but current we have to add up the individual currents. Okay, and this is the Ohm's law. Guys, another note about the Ohm's law: V is equal to what? IR. But for example, V, if we have V, to find V total, we have to use I total and R total. To find potential difference across the voltmeter, VV is equal to IV RV. To find potential difference across a meter, IA RA. Okay? To find potential difference across resistor is equal to current across resistor and resistance across the resistor, or the resistance of the circuit. This is Ohm's law. Look at question 23. We have two questions about the galvanometer. The first question, question 23 in review assess, we want to use a meter. Okay? So we want to use what? A meter of internal resistance. This is question 23. The internal resistance of the ammeter, RA. What do you mean by RA? The internal resistance of what? Of ammeter is equal to what? 5 ohm. The internal resistance of ammeter is 5 ohm. RA is 5 ohm. In order to measure electric currents of intensities up to 10 ampere. I total, the current, the intensity of the current of the source, I total is equal to 10 ampere. Okay, this is I total. While the ammeter measures currents between 0 and 1. What is the maximum current that can be measured by this galvanometer, by this ammeter? Is 1 ampere. Sorry, by the ammeter. Is what? 1 ampere. I across ammeter, the maximum value of the ammeter that can measure is what? 1 ampere. IA, the current across ammeter is 1 ampere. What is the resistance of the shunt? What do you mean by resistance of the shunt? RS is equal to what? The resistance of the shunt in ammeter must be connected in parallel connection. And this resistance must be low resistor. Should be connected in what? Parallel connection. Why? Because V is constant, R and I inversely proportional. In order to do this job. Okay. What is unknown? RS. Guys, listen carefully, please. How can you determine RS? By using the Ohm's law. But before using the Ohm's law, in parallel connection, which one is constant? Potential difference or current? Potential difference. Okay, in parallel connection, the potential difference are constant. So V, can we say the potential difference across ammeter is equal to potential difference across resistor? Yes, of course. Why not? The potential difference across ammeter is equal to the potential difference across the resistor. VA is equal to VR. Why? Because in parallel connection. In what? In parallel connection. Okay. VA is equal to what? Is equal to IA RA. How about VR? IR, I across R across R, it means that shunt. What is unknown? The shunt is unknown. RS is equal to what? Rearrange this equation. Is equal to IA RA over IR. Okay, we rearranged the equation. Now we have to find the resistance across the shunt. Do we have IA? Yes, we have 1 ampere. Do we have RA? Yes, 5 ohm. How about IR? Do we have current across the resistor? No, we don't have current across the resistor. In parallel connection, guys, in parallel connection, I total, if you remember, is equal to what? Look. In parallel connection, I is equal to what? I total is equal to I1 plus I2 plus I3. Look. In parallel connection, I total is equal to I across ammeter plus I across resistor. Do we have current, the total current? Yes, 10 ampere. Total current, 10 ampere. Do we have current across the ammeter? Yes, 1 ampere. Do we have current across the resistor? No. How can you find I across the resistor? Rearrange the equation. Move this one to the other side. It becomes negative 10 minus 1. I across the resistor is equal to what? 9 ampere. 9 ampere passes through the resistor. Replace into this equation. R shunt, IA 1 ampere, RA 5 ohm, IR we didn't have, but we found it 9. 5 divided by 9 is equal to 0.55 ohm. This is the resistor across the circuit and the shunt across the circuit that can be connected in order to convert galvanometer into ammeter. This way you can find and determine the resistance across the shunt. Question 34, guys, look. Question 34, the question says, a moving coil voltmeter measure potential differences between 0 and 5 volt. The maximum volt in this voltmeter is 5 volt. Question 34. Potential difference across the voltmeter is equal to 5 volt. This is V sub V. What do you mean by V sub V? Potential difference across the voltage is 5 volt. We have two unknowns, two branches. If the resistance of the voltmeter is 500 ohm, the resistance of the voltmeter, RV, is equal to what? 500 ohm, sorry. 500 ohm. Calculate the intensity of the current through it if it reaches 5 volt. Calculate what? The current across this voltmeter. A, current is equal to what? According Ohm's law, V is equal to what? IR. VV is equal to IV, RV. What is unknown? IV. IV equal to what? VV over RV. VV is equal to what? 5 volt. RV is equal to what? 500. 5 divided by 500, 0.01 ampere. So what is this? This is 0.01 ampere for the voltmeter, and in a voltmeter, the resistance must be connected in a series connection in order to change galvanometer into a voltmeter. Branch B, we want to use this voltmeter to measure potential difference. We want to use this voltmeter to measure what? Potential difference. Guys, look. In branch B, let's make a table. Okay. We want to use this voltmeter to measure potential difference greater than 5 volt. What is the resistance of the resistor? Resistance is unknown. That should be connected in which connection? Series connection, guys. In series connection, V total is equal to what? V across voltmeter is equal to V across resistor. But I total in series connection is equal to I across voltage, I across resistor. and is equal to 0.01 ampere. We found IV, IR, IT, all are the same because in series connection the current doesn't change. Okay. So with the voltmeter, in order to measure a total potential difference 3 volt and the second time 150 volt. When VT is equal to 30 volt, what is the value of R? And when VT is equal to 150 volt, what is the value of R? Okay, so we have to resistance a couple of times because we have two total potential difference, 30 volt and 150 volt. Guys, in series connection, which one is constant? The current. V is equal to what? IR. At constant current, what is the relation between potential difference and resistance? The relation between potential difference and resistance is directly proportional. More volt has more resistance. Which one has more volt? This one. So which one has more resistance? This one should has more resistance and this one has less resistance. Which one has greater resistance? The V total with 150 or 30? Absolutely the 150 volt. Why? Because V and R is directly proportional in a series connection. In series connection, when V total is 30, V total is equal to what? Voltmeter across voltage across the voltmeter plus voltage across resistor. What is unknown? Resistor is unknown. The resistance is unknown. Do we have V total? Yes, 30. Volt across voltmeter, yeah, we have 5 volt. And also it was mentioned here, the potential difference across the voltmeter is 5 volt. VR, we don't have. VR is equal to what? Rearrange 30 minus 5. VR is equal to 25 volt. Okay? VR is equal to what? 25 volt. And according to Ohm's law, VR is equal to what? IR times R. R is equal to what? Is equal to VR over IR. Do we have VR? We didn't have, but we found 25. IR, yeah, we have it. 0.01 ampere is equal to what? 0.01 ampere. This is the current for all items, okay? Divided by 0.01. R is equal to what? Is equal to 2,500 ohm. This is high resistance connecting in series connection with the galvanometer. The second part, when V total is equal to 150, so you have to do the same process. V total is equal to what? V across voltmeter plus V across resistor. V total in this case 150. V across voltmeter 5 volt. VR unknown. Okay. VR is equal to what? 150 minus 5. VR is equal to 145 volt. And according to Ohm's law, VR is equal to I sub R times R. R is equal to what? Rearrange VR over IR. Replace VR 145. IR is constant 14,500 ohm. This is the resistance when the V total is 150 volt. Okay. So we have done these two questions about the galvanometer. Let's solve the questions. We finished this section. Thanks for God. And now we are going to solve the questions of the section review in section 3, chapter 5. Question 1, a particle. The question is about particle, guys. It's very important to recognize the question about the current conductor or particles. The particle with the charge, this is Q. Experiences a magnetic force, this is force. While moving at right angle, angle is 90, maximum magnetic force. To a uniform magnetic field, if the speed of the charge is 620 meter per second, what is the magnet of the magnetic field? The particle pass through it. Because the question is about the particle, magnetic force is equal to what? QVB sine theta. How about B? You have to rearrange. Magnetic force over QV. Do we have magnetic force? Yes. 1.5 divided by 0.03 times 620. Magnetic field is equal to 8.1 times 10 power negative 2 Tesla. This is question 1 in section review. Question 2, an electron an electron is moving north, encounters the direction of the electron is directed to the north. This is the direction of the charge, the velocity of the electron directed to the north. Uniform magnetic. If the magnetic field points east, field points to east, because the type of the charge is electron, so we have to use this side of our hand. Okay, this is the direction of V, and this is magnetic field, and this is the force of the electron and the force on the electron. V is upward, and the magnetic field is into the east. V north, B east. Where is force? Out of the page. Okay, outward. Magnetic force is outward. Outward, it means Z positive. Okay, Z positive. Out of the page, it's upward, out of the page. Question 3. A straight segment of wire has a length. This is length, was given in centimeter. Be careful, you have to convert to meter, and carries a current 5 ampere. This is I. If the wire is perpendicular, angle 90, magnetic force is maximum, and this is magnetic field. What is the magnetic force? Just replace BIL, 0.75 Newton. Two parallel wires, charges moving in the same direction. Is the force between them attractive or repulsive? If the two charges are moving in the same direction, it means that the two currents are also in the same direction. When the current is in the same direction, the force becomes attraction force. We studied in the two parallel wires. Question 5, guys, look at this question. Very good question. Find the direction of the magnetic force on the current carrying wire. We have a wire, okay, and current runs in this direction, upward to the north, and we have a magnetic field north south. Okay, so do we have the direction of the current? Yes, directed to the north, up. Okay, so how about the direction of the magnetic field? Do we have the direction of the magnetic field? Yes. By this two magnetism, we can find the direction of the magnetic field. The magnetic field lines is usually comes out from the north pole and into the south pole. Here, the magnetic field is directed upward here, okay? So where is the direction of the magnetic field? Is directed to the west. So this is current, okay? This is current upward, thumb. And B is directed to the west. Where is magnetic force? The magnetic force is out of the page. Z positive. The magnetic force is in the Z positive, okay? The MRI is skipped. It's not included for the exam. Guys, we finished chapter 5. Now we are going to solve the question of the standardized test brief. So the question of the test brief are very important. Pay attention. So you have to solve these questions very carefully and very attentively. How can you increase the strength of the magnetic field inside the solenoid? The smart student, the smart student always, they use the equation. By the equation, you can find and you can determine how can you increase the magnetic field inside the solenoid. What is the equation of solenoid? If you remember in section 2, we studied mu naught Ni over L. A, increasing number of coil per unit length, N over L. By increasing N over L, magnetic field increases? Yes, of course. B, increasing current. By increasing current, also field increases? Yes, absolutely. C, place an iron rod inside the solenoid? Of course, because by inserting an iron rod, the magnitude of the permeability increases. All of the above? Yes, all of the above are correct. Is correct, sorry. Okay. Question 2, how will the electron move once it passes into the magnetic field? This is electron, okay? So we have to consider the side of our hand. This is the direction of the V and this is B. Where is force? The electron moves in a semicircle, okay? Why? Because there is no magnetic field here. The electron deflected into the right in a half circle. It will curve to the right, yes. Continue moving, no. So A is not correct. It's right, it will curve to the right, but not continue straight line, straight at the right. It will curve to the left, no. It will move in clockwise semicircle. This is clockwise, this is clockwise or counterclockwise? This is clockwise. Clockwise semicircle, yes. It will move counter, no. The correct answer is what? C. Question 2, C is correct. 2, C is correct. Question 3, what will be the magnet of the force on the electron once it passes into the magnetic field, QVB? This one is correct. Magnetic force is equal to QVB. This is charge, moves at a speed. This is V, magnetic field perpendicular, angle 90, and this is B. What is the magnetic force? QVB. Just replace. It's very easy. Use the passage below to answer question 5 and 6. This is L, 25 centimeter, convert to meter. This is current I. From east to west, the direction of the current is directed to where? To the west. This is I. Earth's magnetic field wires at the location has a magnitude 4.8 and is directed from south to north. Magnetic field to the north. Because we have a wire. This is magnetic field. Okay. So this is magnetic field here. And this is current. The force is into the page. Okay. Downward toward the earth. D is correct in the direction. And how about the magnitude of the magnetic force? So you have to use this relation. B-I-L. Do we have B? Yes. Do we have I? Yes. Do we have L? Yes. So it is direction. Question number 6 is D. Okay, into the page, down toward the earth. Question 7, we have two parallel wires. Wire 1 carries current I1 and creates magnetic field B1. And creates F2. B1 creates what? F1. Guys, wire 1, I1 creates B1 and B1 creates what? F2. But I2 creates B2 and creates F1. What is the direction of the magnetic field B1 at the location of wire 2? B1 on wire 2 is perpendicular always. B1 perpendicular to I2. B2 perpendicular to I1. Perpendicular, it means that out of the page. What is the direction of the magnetic field B1 at location wire 2? At wire 2, here, current is in downward. Here is into the page, here is out. Here is into the page and here is out. At the location of wire 2, the dot is out of the page. Out of the page. D is correct. What is the direction of the force on the wire 2? How many currents do we have? Two currents. Run in opposite direction? Yes. In opposite direction. In, out, becomes repulsion force. The force becomes what? Repulsion force. And what is the direction of the magnetic force on wire 2? Wire 2 is directed to where? Right. To what? To the right. Question 8, B is correct. Because the two current runs in opposite direction, these two wires repel each other. F2, it goes to the right, and F1, it goes to the left. What is the magnet of the magnetic force on wire 2? On wire 2, F1 is equal to, we have to use B2, I1, L1. Okay? F1 is equal to B2, wire 2, the magnetic force F2 is equal to B1. Sorry, we have to find F2. F2 is equal to B1, I2, L2. B1, I2, L2, C is correct. Describe how to use the right-hand rule to determine the direction of the magnetic field around the current carrying wire by using right-hand rule. Thumb is the direction of the current and the forefinger is the direction of the magnetic field. Concentric circle. Draw a diagram showing the path of the positively charged particle moving in the plane of the piece of paper if a uniform magnetic field is coming out of the page. The magnetic field is out of the page. If the magnetic field is out of the page, the positively charged, how is moving the positively charged particle? Guys, look, the positively charged particle, charged particle it should be moving out of the page. The field is out of the page. When the moving like in this direction upward, the positively charged particle is moving clockwise direction. Clockwise direction. If magnetic field is into the page, out of the page, Z positive charge becomes clockwise, negative charge counterclockwise. Okay? Because the magnetic field is out of the page, the positive charge always moves at a circle clockwise in a magnetic field. Question 12. This is the last question. A proton, 1.6 times 10 power negative 19. This is charge of proton. Uniform magnetic field 0.25. Okay. B is equal to 0.25 Tesla. The proton moves clockwise. When does proton moves clockwise? When the magnetic field is out of the page. So because the proton moves clockwise, so this magnetic field is out of the page. Why? Because whenever the proton moves clockwise, the direction of the magnetic field should be out of the page. With the tangential speed, so this is the speed, 2.8 times 10 power 5 meter per second. What is the direction of the magnetic field? And explain how you determine this. Okay? The direction of the magnetic field is out of the page. Why? Because the proton moves clockwise, out of the page. What is the radius of the circle? Because the charge is moving in a circular path. Okay? So the magnetic force, the centripetal force provided by the magnetic force. Okay? And magnetic force is equal to Fc. Magnetic force is equal to what? QVB. Fc is equal to mv square over r. V with V cancel. What is remain? QB mv over r. R is equal to what? mv over QB. Do you have mass? Yes. Mass of proton must be given. Velocity we have, charge and magnetic field we have, and R is equal to 12 times 10 power negative 3 meter. So we finished it, chapter 5. Thank you for listening. I hope you get benefited from my lessons, and keep up your best doing. Inshallah, in the next lesson, we will start explaining the chapter 6 about the Faraday.